On December 27, 2004, scientific instruments on Earth recorded an unusual event. It was a powerful stream of gamma radiation. The source was located 50,000 light-years away in the constellation Sagittarius. The event was brief and lasted only 0.2 of a second. But during this time, a huge amount of energy was wasted. Calculations showed that its volume was equal to the energy emitted by our Sun over a period of 150,000 years. The flow was so strong that it had a measurable effect on the Earth's ionosphere. The ionosphere is the upper layer of our planet's atmosphere. Gamma rays caused its partial ionization. This is a rare case where an object on the other side of the galaxy has directly influenced the physical state of our planet. The event was named GRB 041227. It was recorded by the Integral and Swift Space telescopes. This gamma-ray burst became the starting point for a new phase in the study of the most powerful magnets in the universe. He clearly demonstrated that there are events whose power is capable of overcoming enormous interstellar distances. The source of this enormous burst of energy was a magnetar. This is a special type of neutron star. Object name SGR 180620. Headlines in the media often describe such objects as a cosmic threat. But this approach is based on emotions. Scientific analysis is needed to truly understand the situation. Our task is to conduct a systematic audit of this potential hazard. Such an audit is similar to a safety inspection of a complex engineering system, such as a nuclear power plant. It consists of several steps. The first step is to identify the object. We need to understand what a magnetar is and what its properties are. The second step is to analyze the threat mechanism. We need to figure out why the flares occur and what their physics are. The third step is to calculate the probability and consequences. We must assess how likely such an event is for Earth and what it will lead to. Only such a methodical approach allows us to separate facts from speculation and obtain an objective risk assessment. To understand what a magnetar is, you first need to understand what a neutron star is. A neutron star is one of the possible final stages in the evolution of a massive star. When a star with a mass greater than 8 solar masses runs out of fuel, it explodes as a supernova. After the explosion, its superdense core remains. This is a neutron star. The mass of this core is approximately 1.5 times greater than the mass of our Sun. At the same time, all this material is compressed into a sphere with a diameter of only 20 or 25 kilometers. That's the size of a small town. The density of matter under such conditions is enormous. It reaches 100 million tons per cubic centimeter. 1 teaspoon of neutron star matter on Earth would weigh about 1 billion tons. That's more than the weight of the entire human race. We are used to massive objects always being large. A neutron star breaks this rule. This is an object with a colossal mass but a very small size. The process of neutron star formation explains another of its properties. This is a very fast rotation. The progenitor star from which it is formed is a huge, slowly rotating object. During a supernova explosion, its core rapidly contracts or collapses. Its radius decreases by tens of thousands of times. The fundamental physical law of conservation of angular momentum applies here. This law can be explained with a simple example. When a figure skater spins on the ice and presses their arms against their body, their spinning speed increases dramatically. The same thing happens with the core of a star. Reducing the radius causes it to spin faster and faster. As a result, a newborn neutron star can rotate dozens or even hundreds of times per second. Thus, a slowly rotating giant generates an ultra-fast and ultra-small object. A magnetar is a special case of a neutron star. Its main distinguishing feature is its extremely strong magnetic field. A normal neutron star already has a strong field, but with a magnetar, it is thousands of times stronger. Such a field arises under certain conditions at the moment of a star's birth. If the progenitor star had its own magnetic field and rotated rapidly, these two factors would create a powerful dynamo effect during the collapse process. Convective plasma flows in the contracting core function as a giant generator. They amplify the magnetic field to a value of 10 to the 15th degree Gauss. This is 1,000 trillion times stronger than the Earth's magnetic field. In ordinary objects, the magnetic field is a passive property. In a magnetar, it becomes the main driving force. The energy stored in the magnetic field of a magnetar is greater than the energy of its rotation. It is this energy that fuels all of its active manifestations. The existence of such a strong field is confirmed by direct observations. The main evidence is the abnormally rapid slowdown in the rotation of magnetars. Any rotating neutron star slows down over time. This happens because a rotating magnet emits energy and loses angular momentum. However, in magnetars, this process occurs much faster than in ordinary neutron stars. Their rotation period increases significantly over several years of observation. Astronomers can measure the rate of this deceleration with high precision. Based on this data, the strength of the object's external magnetic field can be calculated. The calculation results correspond to the values predicted by the dynamo effect theory. Thus, we do not simply assume the existence of a field. We can observe its activity in real time by how it slows down the rotation of the star. The magnetic field of a magnetar is so strong that it changes the shape of atoms themselves. Under normal conditions, electrical forces are responsible for the shape of an atom, making it spherical. But in the magnetar field, magnetic forces become dominant. They stretch the electron shells of atoms along lines of force. As a result, the iron atom on the surface becomes like a needle, hundreds of times thinner than its normal form. This means that normal chemical reactions are impossible there. Chemistry is based on the interaction of spherical electron shells. When the shells are stretched, these interactions change completely. The substance on the surface of the magnetar consists of one-dimensional chains of atoms. Its properties are unlike anything we can create in a laboratory. This is a fundamental change in the structure of matter where the laws of chemistry we are familiar with cease to apply. The magnetic field of a magnetar is not static. It evolves over time. This creates enormous tension in his cortex. The crust of a neutron star is a solid layer about 1.5 kilometers thick. It consists of a crystal lattice of atomic nuclei. The magnetic field is as if frozen into this crust. The internal magnetic field of an object has a more complex and intricate structure than the external one. Over time, it tends toward a simpler state. This movement of the internal field pulls along the lines of force, frozen into the crust. As a result, the bark twists and deforms. Mechanical stress accumulates in it. This process can be compared to how tectonic plates on Earth accumulate stress before an earthquake. The stress in the magnetar's crust increases until it exceeds the material's strength limit. When the stress in the bark exceeds its strength limit, fractures occur. These events are called starquakes. The mechanism is similar to earthquakes on Earth, but the scale of energy is incomparable. The rupture of the magnetar's crust releases energy in two ways. First, powerful seismic waves arise that pass through the entire star and cause it to oscillate. Secondly, a sharp displacement of the crust leads to a change in the external magnetic field. This change generates a burst of X-rays and gamma rays. The starquake model provides a good explanation for the regular but relatively weak bursts of magnetars. The energy released in a single such event can exceed the energy of a solar flare by 1,000 times. But even this power is not enough to explain the most gigantic surges, such as the one observed in 2004. Giant flares are explained by a different mechanism. It is associated with the restructuring not of the crust, but of the outer magnetosphere of the magnetar. The magnetosphere is the region around a star where its magnetic field dominates. Due to the movement of the crust and the internal field, the lines of the magnetosphere can become severely twisted and tangled. They accumulate enormous energy. This process is similar to twisting rubber hoses. At some point, the field configuration becomes unstable. A sudden event occurs, called magnetic reconnection. The twisted lines of the field break apart and reconnect, forming a simpler and more stable configuration. Excess energy is released almost instantly. It turns into heat radiation and accelerated particles. This mechanism is responsible for the most powerful flares. A similar process causes solar flares, but in a magnetar it is billions of times more powerful. These same mechanisms are also responsible for other mysterious signals from space. We are talking about fast radio bursts, or FRBs. These are very short but extremely powerful pulses of radio waves that come from distant galaxies. For a long time, their source was unknown. Magnetars were considered one of the main candidates. In April 2020, this hypothesis was directly confirmed. Radio telescopes have detected a rapid radio burst from the magnetar SGR 1935+2154, which is located in our Milky Way galaxy. Simultaneously with the radio burst, X-ray telescopes recorded a flash from the same object. This observation became decisive evidence. It showed that at least some of the fast radio bursts are indeed generated by magnetars during their periods of activity. This discovery brought together two areas of high-energy astrophysics. All these phenomena, starquakes, giant flares, and fast radio bursts, are fed from a single source. This source of energy is the magnetic field of the magnetar itself. Unlike many other active objects in the universe, a magnetar does not need an external energy source. For example, X-ray pulsars shine by pulling matter from a companion star. Active galactic nuclei get their energy from matter falling into a supermassive black hole. Magnetar, on the other hand, consumes its own internal energy reserves. Each flare is a small step in the process of its magnetic field decaying. Thus, the most vivid and turbulent events occur at a facility that is slowly dying. His activity is a sign of irreversible energy loss. When the field's energy is depleted, the magnetar will become a normal, calm remnant of a star that is invisible to us. Now that we understand the mechanism of outbreaks, we need to assess their impact factors. The main threat from a magnetar to life on another planet does not come from gravity. It originates from a stream of hard gamma radiation. Gamma radiation is a form of electromagnetic radiation, just like visible light or radio waves. But its photons or quanta carry millions of times more energy. The energy of a single gamma quantum exceeds 100,000 electron volts. This energy is sufficient to break chemical bonds in molecules and ionize atoms. This threat is completely invisible to the human eye. It spreads at the speed of light. This means that there will be no warning period between the moment of the flare and its impact on the planet. The gamma quantum flux is the main damaging factor that we will analyze. The main target for gamma radiation in the planet's atmosphere is the ozone layer. This layer is located in the stratosphere and protects the surface from the sun's harsh ultraviolet radiation. Gamma quanta interact with nitrogen molecules, which are the most abundant in the atmosphere. They ionize nitrogen and trigger a chain of chemical reactions. First, the nitrogen molecule N2 breaks down into two separate atoms. These atoms then react with oxygen to form nitrogen oxides, such as NO. Nitrogen oxides are very effective at destroying ozone. They act as catalysts. This means that a single nitrogen oxide molecule can participate in the reaction many times, destroying thousands of ozone molecules while remaining unchanged. Thus, gamma rays do not burn ozone directly. They trigger a catalytic mechanism that leads to rapid and large-scale destruction of the ozone layer. The consequences of the destruction of the ozone layer will be catastrophic for the biosphere. If the ozone layer decreases by 50% or more, the level of ultraviolet radiation on the surface will increase dramatically. This will lead to the death of phytoplankton in the oceans. Phytoplankton is the basis of the marine food chain and produces most of the oxygen on the planet. Its demise will cause the collapse of marine ecosystems. The consequences for life on land will be no less serious. Strong ultraviolet light damages the DNA of living organisms. This will lead to mass mutations and cancer in animals. Plants will also suffer from burns and impaired photosynthesis. It is important to understand that the magnetar flare itself lasts only a few seconds. But its biological consequences will unfold over many years and decades after the event. The damage depends on the dose of radiation received, and the dose depends on the distance from the source. Scientists use data on the SGR 1806-20 magnetar flare to calculate the safe distance. Their calculations showed that if such an event occurred 10 light-years away from us, it would lead to the destruction of most of the ozone layer. Such an event would cause mass extinction on Earth, comparable to the greatest catastrophes in its history. This distance of 10 light-years can be conditionally called the kill zone or death zone. Our main protection against such events is the inverse square law. It states that the intensity of radiation decreases proportionally to the square of the distance. If the distance is doubled, the flow rate will decrease fourfold. This sharply limits the space in which the magnetar poses a real threat. Gamma radiation is the main but not the only damaging factor. The magnetar flare creates other effects as well. One of them is a powerful electromagnetic pulse, or EMP. Such an impulse can disable all electronics that do not have special protection. It is dangerous primarily for satellites in Earth orbit. Satellite failure will lead to the immediate shutdown of GPS navigation systems, global communications, and financial transactions. Another factor is the stream of charged particles that accompanies the flash. These particles create secondary radiation when they enter the atmosphere. Thus, the threat from a nearby outbreak is complex. It affects both the biosphere and the technosphere. Even if the consequences for life are not fatal, the destruction of the technosphere could set civilization back hundreds of years. Now, let's assess the current situation based on the available data. Astronomers are constantly searching for and cataloguing magnetars. Today, the closest known magnetar to us is called XTE J18 Cor 197. It is located about 8 or 9,000 light-years away from the solar system. This distance exceeds the calculated damage zone of 10 light-years by a factor of hundreds. Consequently, none of the magnetars known today pose a direct threat to us. It seems that we are completely safe. But there is an important point of uncertainty here. We only see active magnetars that manifest themselves as flares. The theory predicts the existence of a large number of dormant inactive objects. We cannot be entirely sure that one of these dormant magnetars is not much closer to us than the known active objects. The problem of dormant magnetars prompts us to ask a question. How many of these objects are there in our galaxy? Observations provide us with only part of the answer. To date, we have discovered and confirmed the existence of about 30 active magnetars, but these are only the objects that are currently manifesting themselves in flashes. Theoretical models of stellar evolution allow us to estimate their total number. Calculations show that approximately 1 in 10 explosions of massive stars produces a magnetar. Based on the rate of star formation in the Milky Way, this means that there must be about 30 million neutron stars with magnetar fields in the galaxy. The vast majority of them are no longer active and invisible to us. They represent a hidden population. We only see the tip of the iceberg. This creates uncertainty in risk assessment. The next step in risk assessment is to determine the frequency of giant eruptions. These are the rarest and most powerful events. Over the past 40-odd years, astronomers have recorded only 3 such flares in our galaxy and neighboring galaxies. The first occurred in 1979, second in 1998, and the third is the most intense flare from SGR 1806-20 in the year 2004. This data allows for statistical evaluation. It shows that a single magnetar produces a giant flare approximately once every 10,000 or 100,000 years. For an individual object, this is a very rare event, but there could be thousands of active magnetars in our galaxy. Considering their total number, one giant flash somewhere in the Milky Way could occur every few decades. We simply don't see most of them because they happen too far away. Now we can combine all the data to calculate the probability of a dangerous event for Earth. To do this, scientists use computer modeling. The model takes into account three main parameters. The first is the spatial density of magnetars in the vicinity of the solar system. The second is the frequency of giant flares, which we estimated earlier. The third is the size of the affected area, which is a sphere with a radius of about 10 light years. The program repeatedly simulates the random distribution of magnetars and their flares in the galaxy over millions of years. The results of these calculations show that the average interval between events dangerous to Earth is about 800,000 years. This is a very large number for human civilization, but on a geological timescale, such an event is statistically probable. This is a classic example of a risk with a low probability but extremely high consequences. To understand what this number means, it must be compared with other known cosmic threats. The most well-known of these is the threat of asteroid strikes. NASA's programs for tracking near-Earth objects allow us to estimate the frequency of such events. It is believed that the fall of an asteroid larger than 1 kilometer in diameter would cause a global catastrophe. This will result in a nuclear winter effect due to dust being released into the atmosphere. Statistics show that such an event occurs on Earth approximately once every 500,000 years. This figure is comparable to the risk from a magnetar, which we estimated at 800,000 years. This means that mathematically, the threat from magnetars is in the same danger class as the threat from large asteroids. We're accustomed to discussing the asteroid threat, but we rarely discuss other astrophysical risks, even though their probability may be comparable. There is one fundamental difference between these two threats. This is the predictability factor. Modern telescopes and survey programs make it possible to detect a large asteroid on a collision course with Earth many years or even decades before the event. This provides a theoretical opportunity to develop and apply technologies to deflect it. The threat posed by asteroids is an engineering problem that can be solved in the future. A magnetar flare, on the other hand, is completely unpredictable. This is a stochastic, i.e., random process. We don't know which magnetar will flare up next or when it will happen. There will be no warning. The signal of the flare will reach Earth simultaneously with the damaging radiation itself. Thus, the threat posed by magnetars is a fundamental risk of nature that we cannot control. Let's consider another astrophysical threat. These are long gamma-ray bursts, or GRBs. They originate from explosions of very massive stars of the Wolf-Rayet type. These events are much more powerful than magnetar flares. Their area of impact can reach several thousand light years. However, their radiation is not omnidirectional. It is concentrated in two very narrow beams, or jets, that burst out from the poles of the star. For such a gamma-ray burst to be dangerous to Earth, it must be located precisely in the path of one of these jets. The probability of such a direct hit is extremely low. Therefore, the overall risk to Earth from such events is estimated to be one event every 10 or 100 million years. This is much less frequent than the threat posed by magnetars. A gamma-ray burst can be compared to a sniper rifle, and a magnetar flare to a fragmentation grenade. The bullet is more powerful, but statistically more likely to be hit by shrapnel. A comparative analysis allows us to draw a conclusion. The risk posed by magnetars is not a dominant astrophysical threat to Earth. It occupies an intermediate position. It is less likely than a large asteroid falling, but it is more likely than a direct hit from a gamma-ray burst jet. Therefore, this risk cannot be considered negligible and completely ignored. But it is also no cause for panic. Scientific assessment places it in the category of unlikely events with high consequences. People often tend to go to extremes when assessing such risks. They either believe that disaster will never happen or that it is inevitable. Reality is usually more complicated. It lies in the field of accurate probability estimates. Studying magnetars allows us to make such an assessment and understand the real place of this threat in the overall list of risks. We assess the threat posed by magnetars. Now, let's look at their evolution and life cycle. Magnetars are very short-lived objects by cosmic standards. Their activity is directly related to the energy of the magnetic field. Each flash and continuous radiation carries away a portion of this energy. The field gradually fades away. Models show that this process takes only 10 or 20,000 years. After that, the magnetic field weakens to the level of a normal neutron star. Activity ceases completely. The object ceases to be a magnetar. It becomes a calm, extinct remnant of a star that is very difficult to detect. It is precisely their short lifespan that explains why we see so few active magnetars in the galaxy. We can only observe those that were born very recently. It's like observing supernovae. We only see the moment of the explosion itself, not the long life of the star before it. The question arises about the future fate of the magnetar. Can such an extreme object end its life by collapsing into a black hole? Theoretically, this is possible for any neutron star. To do this, its mass must exceed a certain limit. This limit is called the Oppenheimer-Volkoff limit, and is approximately 2/3 of the mass of the Sun. If a neutron star gains additional mass and exceeds this limit, it will collapse into a black hole. This usually occurs in binary systems where a neutron star pulls matter from its companion star. However, most known magnetars are single objects. They do not gain mass, but, on the contrary, lose it through radiation. Therefore, such a collapse scenario is unlikely for them. Instead of a dramatic transformation into a black hole, a quiet end awaits them. They simply cool down and fade away, becoming invisible. Although magnetars are associated with destruction, they can also play a constructive role in the universe. We are talking about the origin of heavy chemical elements such as gold and platinum. The merger of binary neutron stars is currently considered to be the primary source of these elements. At the moment of fusion, conditions are created for the rapid neutron capture process, or R process. It is during the R process that the heaviest elements of the periodic table are born. Some scientists suggest that similar conditions may arise in matter ejected during giant magnetar flares. If this hypothesis is correct, magnetars also contribute to the enrichment of the galaxy with heavy elements. Thus, an object capable of destroying life on a planet simultaneously participates in the creation of the elements that ultimately make up the planets themselves and the life on them. Studying such distant and extreme objects requires special instruments. We cannot study magnetars directly. We obtain all information from analyzing their radiation. Magnetars emit mainly in the high-energy part of the spectrum. These are X-rays and gamma rays. The Earth's atmosphere is opaque to this type of radiation, so all observations are made using space telescopes. Observatories such as Chandra, XMM Newton, Swift, and Fermi constantly observe the sky. Some of them operate in a mode that monitors the entire sky. They constantly scan space, waiting for short, bright flashes. When such a flare is detected, the system automatically sends an alert to all other telescopes around the world. They quickly locate the source to gather as much data as possible. The main problem in studying magnetars is the unpredictability of their activity. In addition to registering flares, there is another method for searching for magnetars. This is known as hunting by indirect evidence. Scientists are not looking for the bursts themselves, but rather for objects with properties characteristic of magnetars. The main sign of this is a significant slowdown in rotation. As we have already mentioned, a strong magnetic field effectively slows down a neutron star. Astronomers can measure the rotation period of radio pulsars and its derivative, i.e., the rate of deceleration. If a pulsar has a very high value for this derivative, this indicates the presence of an extremely strong magnetic field. Such an object becomes a candidate for a magnetar even if it does not exhibit flare activity at the moment. This method allows dormant or inactive magnetars to be found. It helps us better understand the overall population of these objects, not just their most active part. Future space missions will open up new opportunities for studying magnetars. Projects for a new generation of X-ray observatories are currently being developed. One such project is the European Space Agency's Athena telescope. It will have a mirror with a huge collecting area and very high-resolution spectrometers. Such instruments will enable the study of magnetars' magnetospheres in unprecedented detail. Scientists will be able to construct maps of the temperature and density of the plasma around these objects. They will be able to observe how the structure of the magnetic field changes before and after the flare. Today, we see a magnetar as a simple point of light. In the future, we will be able to study the physical processes in its environment in as much detail as we study the processes on the Sun today. This will give us the key to accurately understanding the mechanisms of their activity and possibly predicting it. Gravitational wave astronomy opens up a whole new window for studying magnetars. Powerful starquakes that deform the crust of a neutron star should emit not only light, but also gravitational waves. Gravitational waves are fluctuations in the fabric of spacetime itself. Detectors such as LIGO and Virgo can detect them. Recording the gravitational wave signal from the magnetar will allow us to literally look inside the star. Light carries information about processes on the surface and in the magnetosphere. Gravitational waves carry information about the mechanical movements of the crust itself and about the properties of the matter in the star's core. This will allow us to test our theories about the internal structure of neutron stars and the state of matter at ultra-high densities. We will be able to not only see magnetars but also hear them. Now we can return to the main question that was posed at the beginning. Should we be afraid of magnetars? After conducting a systematic analysis, the answer becomes clear and unambiguous. No, but we are obliged to study them. This conclusion is based not on emotions, but on a combination of facts and calculations. Fear often arises from uncertainty or incomplete understanding of the scale of a phenomenon. The initial information about the outbreak in 2004, which exceeded the power of the sun's radiation over hundreds of thousands of years, is truly shocking. But a scientific approach requires moving beyond first impressions to a comprehensive analysis. A simple yes or no answer is insufficient for such a complex topic. Instead, an approach known as risk analysis is used, where any phenomenon is evaluated according to two parameters. The first is the probability of an event. The second is the severity of its consequences. Magnetars fit perfectly into this scheme. The consequences of their close outbreak are extremely high. However, as we will show below, the probability of this event occurring is extremely low. Our final verdict will be based on three key arguments, which we will examine in great detail. This argument is based on distance, probability, and comparison with other risks. The first and most important argument is distance. Our main protection against most astrophysical threats is the vast scale of space. The area affected by the giant magnetar flare is estimated to be approximately 10 light-years. Inside this zone, the consequences for the ozone layer would be catastrophic. Let's take a look at our immediate stellar environment. The closest star to us is Proxima Centauri, just over 4 light-years away. It is a red dwarf that will never become a neutron star. Other neighbours are the Alpha Centauri system and Barnard's star. None of them are massive enough to become a magnetar. The solar system is located in a region of the galaxy with a relatively low density of stars. This area is known as the local bubble. This is a region of rarefied and hot interstellar gas. The probability that there is a neutron star within 10 light-years of us that we have not yet detected is extremely low. Modern astronomical surveys, such as the Gaia mission, have mapped the positions and movements of billions of stars with the highest precision. Distances to them are measured using the parallax method. This is a geometric method based on the displacement of a star against the background of distant objects as the Earth moves in its orbit. Although it is very difficult to detect a single cold neutron star, its gravitational influence on neighboring objects or its accidental passage in front of a distant star would most likely be noticed. Thus, the emptiness of interstellar space and the inverse square law are our main shields. The second argument is the probability of the event itself. The final risk is the product of several independent and very small probabilities. Let's examine them step by step. The first is the possibility of a magnetar being dangerously close. Based on the density of stars in our part of the galaxy, scientists estimate this probability to be extremely low, perhaps 1 in a million. The second is the probability that this hypothetical nearby magnetar is active right now. We know that the active phase of a magnetar lasts only 10 to 20,000 years. This is an insignificant moment compared to the 13 billion years of the galaxy's existence. The probability of catching him in the active phase is less than 1 in a million. The third possibility is that this active and nearby magnetar will produce a giant flare in the near future. We know that the frequency of such outbreaks for a single object is approximately once every 10,000 years. If we multiply all these small probabilities together, the final number will be astronomically tiny. This is much less than the probability of winning a major lottery several times in a row. People don't take such small chances well, but it is precisely on them that all safety assessments in complex systems, from nuclear energy to aviation, are based. Although the event is theoretically possible, its probability over the lifetime of human civilization tends towards zero. The third argument is context and comparison with other risks. Humanity's resources for preventing global threats are limited. Therefore, it is important to set priorities correctly. To do this, you can create a conditional risk table. The first level will include threats with a high probability and preventable consequences. These include, for example, anthropogenic climate change and global pandemics. The second level will include threats with a low probability but which are potentially preventable. This includes the impact of an asteroid larger than a kilometer or the eruption of a supervolcano. Such events occur once every hundreds of thousands of years. The third level will include threats with a vanishingly small probability that are completely unpredictable and unavoidable. This is precisely where magnetar flares and nearby gamma-ray bursts fall. Rational resource allocation requires addressing first and second level threats first. Investing in planetary defense systems against asteroids is a higher priority than developing hypothetical shields against gamma radiation. There is a concept of opportunity cost. Every dollar spent on protecting against an extremely unlikely threat is a dollar that was not spent on solving more pressing problems. The study of magnetars is important not so much because of the threat they pose as because of their unique scientific value. These objects are natural laboratories for testing fundamental laws of physics under extreme conditions. First, it is a test of quantum electrodynamics. There is something called the Schwinger limit. This is the electric field strength at which the vacuum becomes unstable and begins to spontaneously generate pairs of particles and antiparticles. The magnetic field of a magnetar is equivalent in energy density to fields that significantly exceed this limit. Magnetars are the only place in the universe where we can observe these effects directly. Secondly, it is a test of nuclear physics. The equation of state of matter inside a neutron star remains one of the greatest mysteries. This is the dependence of pressure on density. It determines how compressible a neutron star is. By observing the fluctuations of magnetars after flares, scientists can impose constraints on this equation. Thirdly, it is a test of the general theory of relativity in a strong field regime where both gravity and electromagnetism are extremely strong. Any deviations from Einstein's predictions would be easiest to detect in such objects. Here we see an interesting paradox of scientific knowledge. The more we learn about the universe, the more potential dangers we discover. Before the invention of the telescope, people feared only comets, considering them bad omens. Later, science turned them into predictable celestial bodies, but it also discovered asteroids and showed that their fall could cause a catastrophe. Similarly, 100 years ago, we did not know about the existence of magnetars and did not worry about them. Now we know, and this adds a new item to the list of hypothetical threats. But the same knowledge also gives us the tools to assess these threats. The discovery of magnetars allowed us to study their properties, calculate their number, and the frequency of their flares. As a result, we were able to conclude that they do not pose an immediate danger. This path from discovery through fear to understanding and assessment is typical for science. Science does not create threats. It simply illuminates the dark corners of the universe and gives us a map of potential dangers, indicating their real rather than imagined scale. So magnetars are a perfect example of systemic risk. They are events with a very low probability but extremely high consequences. Studying them teaches us an important skill: the skill of taking a rational approach to complex and unlikely threats. This skill is key to the long-term survival of any technological civilization. We live in a complex and not always predictable universe that is neither hostile nor friendly. It simply obeys the laws of physics. Our only tool for survival and prosperity in it is the scientific method. It allows us not to fear the unknown, but to systematically study it, analyze it, and draw conclusions. This is not just an academic exercise, it is a fundamental aspect of security. Understanding space is the highest form of risk assessment for humanity. The final choice for each of us is to succumb to an irrational fear of the incomprehensible power of nature, or to use our minds to analyze it and understand our place in the universe. To understand why starquakes occur, we need to take a closer look at the structure of a neutron star's crust. It is not just a solid shell. Models show that just below the surface there is a layer of matter in an exotic state called nuclear paste. In this state, under enormous pressure, the forces of nuclear attraction and electrical repulsion between protons and neutrons compete in a complex way. As a result, nucleons form ordered structures of various shapes. Depending on the depth and density, these can be droplets similar to gnocchi, cylinders similar to spaghetti, or flat sheets similar to lasagna. This substance has tremendous strength and elasticity, far exceeding the strength of any material on Earth. It is the properties of nuclear paste that determine the strength limit of the crust. When the stress from the twisting magnetic field exceeds this limit in the nuclear paste layer, fractures or shifts occur, leading to a starquake. According to quantum electrodynamics theory, the vacuum is not completely empty. Pairs of virtual particles and antiparticles constantly appear and disappear in it for a very short time. The super strong magnetic field of a magnetar affects these virtual electron-positron pairs. It orders them by lining them up along lines of force. Because of this, the vacuum itself begins to affect the light that passes through it. This effect is called vacuum double refraction. When light passes through such a magnetized space, it splits into two components with different polarizations, as if it were passing through a crystal of Iceland spar. Recent observations using the IXPE X-ray polarimeter have measured the polarization of radiation from a magnetar for the first time and confirmed this effect. This proves that even empty space near a magnetar has measurable optical properties. The vacuum ceases to be empty and becomes an active medium. Let's take a closer look at the SGR 1806-20 burst in 2004. Analysis of its light curve, i.e., the graph of brightness versus time, revealed a complex structure. First, a very short initial peak lasting only 0.2 of a second was recorded. It contained most of the energy and had a very hard spectrum. It was followed by a longer and softer tail of radiation. This tail lasted about 400 seconds, and its brightness changed periodically. The period of these pulsations was 7.56 seconds, which exactly matched the known rotation period of the neutron star itself. The temperature in the tail was estimated to be approximately 2 billion degrees Kelvin. This complex structure indicates several physical processes. The initial peak was caused by a magnetic reconnection event in the magnetosphere. The pulsating tail is radiation from a hot electron-positron plasma cloud that was created by the flare, captured in the magnetosphere, and rotated with the star, gradually cooling down. Magnetars are just one example of extreme neutron stars. To understand their uniqueness, we can compare them to other objects, such as black widow pulsars. A black widow is a millisecond pulsar in a closed binary system. It rotates at tremendous speed and has a strong stellar wind. This wind consists of relativistic particles, i.e., particles moving at nearly the speed of light. The flow of these particles bombards the companion star and literally evaporates its matter. The mass of the companion star in such systems is often only a few dozen times that of Jupiter, which indicates its almost complete destruction. The key difference is that a magnetar is extreme because of its internal energy stored in its magnetic field. A black widow is extreme because of its interaction with its environment, i.e., because of an external energy source. This shows that neutron stars can be very different depending on their evolutionary path. The magnetic field of a magnetar is capable of creating antimatter on an industrial scale. During a giant flare in the magnetosphere, a so-called fireball is formed. This is a dense cloud consisting of electron-positron pairs and photons. A positron is an antiparticle of an electron with the same mass but a positive charge. These pairs are born directly from the energy of the magnetic field. The strongest field can spontaneously transform into matter and antimatter according to Einstein's equation EmC2. A fireball can reach thousands of kilometers in size and is held by the magnetosphere for several minutes. The gamma radiation we observe is the result of annihilation, i.e., the mutual destruction of electrons and positrons in this cloud. During annihilation, their mass is completely converted into energy in the form of gamma quanta. Thus, antimatter is not something exotic near a magnetar. It is produced in huge quantities and is a key component of the most powerful processes observed. Magnetars may also be linked to another fundamental mystery: the problem of dark matter. One hypothesis for explaining it suggests the existence of very light particles called axions. Axions are one of the leading candidates for dark matter particles. According to this theory, photons in a very strong magnetic field can transform into axions and vice versa. This process is called the Primakov effect. If this is the case, then the core of a magnetar, where there are both photons and a strong field, must be a powerful factory for the production of these hypothetical particles. Axions hardly interact with ordinary matter, so they freely leave the star, carrying energy with them. Their birth in a magnetar should leave certain traces, for example, leading to faster cooling of the object than predicted by standard models. Searching for such anomalies in the temperature of neutron stars is one way to indirectly detect axions. The activity of magnetars is also important for the SETI program, which searches for extraterrestrial civilizations. When the first pulsar was discovered in 1967, its regular signals were initially mistaken for artificial ones and named LGM-1, short for little green men. Later, it became clear that this was a natural astrophysical object. Fast radio bursts from magnetars pose a similar problem. These are very short and powerful radio signals. In terms of their characteristics, they can be similar to the artificial signals we expect to find, for example, from an interstellar beacon. Therefore, one of the main tasks for SETI is to learn to distinguish natural signals from magnetars from potential techno-signatures. On the other hand, magnetar bursts can interfere with the search. They create radio noise that can mask or drown out weaker artificial signals. Thus, magnetars are another example of how exotic but natural astrophysical phenomena complicate the search for traces of intelligence in the universe. Calculating damage to the ozone layer is a complex task. Scientists cannot simply use a single formula. They apply complex three-dimensional models of atmospheric chemistry and dynamics. One such model, developed at the US National Center for Atmospheric Research, is called WACCM. Initial conditions such as atmospheric state, season, latitude, and gas concentration are entered into this model. Then an external factor is added, a short but powerful stream of gamma radiation with a specific energy. The program calculates step by step how this stream ionizes nitrogen, how nitrogen oxides are formed, and how they spread throughout the atmosphere with the help of stratospheric winds. These same models are used to predict the effects of nuclear winter or the impact of chlorofluorocarbons on the ozone layer. Only such detailed modeling allows for an accurate assessment of the damage to the ozone layer in different regions of the planet. Even if the magnetar flare does not destroy the biosphere, it will have an immediate impact on our technology. The flare in 2004 caused measurable disturbances in the D layer of the ionosphere at an altitude of 60 to 90 kilometers. This layer is important for the propagation of long radio waves used in some communication and navigation systems. A more powerful and closer flare would cause much stronger ionization of the entire ionosphere. This would lead to a complete disruption of the GPS and GLONASS global positioning systems. These systems operate by receiving ultra-precise time signals from satellites. The ionosphere slows these signals down slightly, and this effect is usually corrected. A sudden change in the state of the ionosphere would render these corrections invalid and lead to huge errors in position determination. All satellite communications would also be disrupted. In today's world, navigation, financial transactions, and communications depend on these systems. Their simultaneous failure would lead to technological collapse. The question arises whether similar events have occurred in Earth's past. Scientists are searching for traces of them in the geological record. Some mass extinctions in Earth's history have no clear explanation. The most famous example is the Ordovician Silurian extinction, about 445 million years ago. It was one of the 5 largest in history. One hypothesis links it specifically to a nearby gamma-ray burst from a supernova, or magnetar. The consequences of such an event correspond to what we see in the rocks. Rapid cooling and an ice age due to the destruction of the ozone layer and the formation of aerosols. The main problem with this hypothesis is the lack of direct evidence. Proof could be found by searching for certain isotopes that are formed only under the influence of gamma rays. However, so far, no such isotopes have been found in rocks from that time. Therefore, the hypothesis remains interesting but speculative. Magnetars continue to surprise us, challenging our theories. In 2012, Magnetar 1E 2259 Pool 586 exhibited abnormal behavior. Its rotation speed decreased sharply over a short period of time. This phenomenon was called an anti-glitch. It is the opposite of the usual behavior of pulsars, which sometimes accelerate sharply. Such accelerations are called glitches. The standard model of a glitch explains it as an interaction between the solid crust and the superfluid core of a neutron star. The core rotates slightly faster than the crust, and from time to time transfers part of its angular momentum to it, causing the crust to accelerate. Anti-glitches do not fit into this model. There is no obvious mechanism that could slow down the rotation so sharply. This was probably due to a powerful restructuring of the magnetic field, which led to the ejection of matter into space, carrying away part of the angular momentum. This mystery still awaits a solution. In addition to photons and gravitational waves, magnetar flares can theoretically be accompanied by neutrino emissions. Neutrinos are very light particles that hardly interact with matter. They are produced in nuclear reactions in the interiors of stars and freely pass through them. If processes in the core of a magnetar associated with field restructuring or starquakes lead to nuclear reactions, they should generate a stream of neutrinos. These particles can convey information to us directly from the center of the object, from regions that are inaccessible for observation in the electromagnetic spectrum. The search for such neutrino signals during flares is one of the tasks of large neutrino telescopes, such as IceCube in Antarctica. Analysis of IceCube data during a magnetar flare in 2020 did not reveal any significant signals. But the search continues. This is part of a new multi-channel astronomy approach, where a single object is studied through several channels of information at once to obtain the most complete picture. According to Einstein's general theory of relativity, not only mass but also any form of energy distorts space-time. The energy of a magnetar's magnetic field is so great that its contribution to this curvature becomes noticeable. Computer modeling shows that because of this, a magnetar must not be completely spherical. It must be slightly elongated along the axis of the magnetic field. Its shape becomes similar to a rugby ball. This deformation is called quadrupole. This distinguishes a magnetar from a normal neutron star, whose shape is determined only by rotation and is flattened at the poles. This deformation is directly related to the ability to emit gravitational waves. Any rotating object with such an asymmetrical shape must constantly emit weak gravitational waves. Thus, a magnetar is an object where the effects of quantum mechanics and general relativity manifest themselves in full force, making it an ideal object for the search for a unified theory of quantum gravity. Fundamental science requires large investments. The cost of a modern space X-ray observatory such as Chandra or the future Athena is several $billion. These amounts are comparable to the cost of building large power plants or bridges. Society always faces the choice of how to allocate resources. How valuable is knowledge about distant objects compared to solving current earthly problems? Proponents of fundamental research offer several arguments. First, such projects drive technology forward. To build a new telescope, it is necessary to develop new detectors, materials, and software that are then used on Earth. For example, Wi-Fi technology grew out of developments in radio astronomy. Second, it broadens our horizons and has educational and cultural value. And knowledge about the universe and our place in it has its own philosophical value. There is no simple answer to this economic and philosophical question. The question of resources brings us to the ethics of risk management. Should humanity spend money and time protecting itself from highly improbable but catastrophic events, such as an asteroid strike or a magnetar flare? Such investments can be viewed as purchasing an insurance policy for the entire civilization. We spend a small portion of our resources today to protect ourselves from potential total destruction in the future. These types of risks are called existential risks. The problem is that people and governments often focus on short-term goals and problems with a planning horizon of several years. Investing in protection against existential risks is an investment in the distant future. Making such decisions requires strategic thinking and a high level of responsibility towards future generations. This is also related to the Fermi paradox. Perhaps one of the reasons we see no traces of other civilizations is that they were unable to cope with such long-term risks in time. In conclusion, it is worth noting one important and encouraging fact. A magnetar cannot appear in our own solar system. To become a neutron star, a star must have a mass at least 8 or 10 times greater than that of the Sun. Our Sun is a single star with a relatively small mass. It has a much calmer fate ahead of it. In 5 billion years, it will exhaust its hydrogen fuel in the core and turn into a red giant. Its outer layers will expand, possibly engulfing the nearest planets. Then it will shed these outer shells, forming a planetary nebula. And in the center will remain its core, a hot and dense white dwarf. A white dwarf is an object the size of Earth, and with a mass about half that of the Sun. Its density is high, but trillions of times less than that of a neutron star. It will simply cool slowly over trillions of years. Thus, by studying magnetars, we are observing the drama that is unfolding in other star systems. Our own planet is safe, at least in this respect.